Okay, so here we are in week 2, you guys. AMT 162. Aircraft assembly and rigging. I have not been able to post videos of the lectures because I just didn't have the right setup on my laptop, but now I got it all fixed. So expect to be viewing more video lectures from here on out. I know I've been providing you guys the slides. Now you will receive these video lectures, and you can take notes as I'm lecturing on whatever subject it is for the day. Aircraft assembly involves the joining of various components and structures that form an entire aircraft, while aircraft rigging generally refers to the positioning and alignment of an aircraft's major subassemblies to produce a synergistic design. So I have a little example written here for you. Airplanes are typically fabricated in a number of major subassemblies. These subassemblies include the fuselage or main body of the aircraft, an empennage, also known as the tail section. We have wings, the landing gear, and an engine section, also known as our power plant. Airplanes are constructed in 5 main parts, which we just went over in the introduction. We got our fuselage or main body. Empennage is also known as the tail section. Wings, landing gear, and our engine or power plant. First of all, the fuselage, main body. This is just a picture from your airframe textbook. That is our fuselage. You don't see any wings attached to it, so it's trying to show you that this section is what is considered the fuselage. That's the name of it. Our empennage, this is our tail section. Wings, and our wings, this is a good diagram in your Jeppesen book that has all of a wing labeled for you. So you have the center of the wing, you have spoilers, outboard flap, inboard flap, trailing edge, so all of that stuff can be on a wing. Landing gear. Okay. Landing gear. We have our landing gear. It's also a major section of our aircraft. And our engine power plant. Different types of structures. We have a truss type and stress skin type. Our truss type, we can have a Pratt type or Warren type. And stress skin type, we have a monocoque type and a semi-monocoque. Definition of terms, so this is just a definition of those 3 types of structures of aircraft. Definition of our empennage, wing rib, and spar. I think I have a typo in this one. Cantilever rings, Sitka spruce, so you guys can review those terms. You should know what those mean. This is another good diagram of some different structures of the aircraft. Has labeled for you here like our bulkhead, skin of the aircraft. These are called formers on a certain type of structure. In this type of structure we have longerons, diagonal web members, vertical web members, and here in this type of structure we have members of the structure such as the firewall, wing attachment points. Stringers are these items that run along the body of the aircraft. We also have formers that run circular 90 degrees to the stringer. A little breakdown of our tail section and wing section. Also with stringers. These are called our wing ribs here. Our wing spar. It's our main spar. So different sections of the aircraft that you guys should be familiar with. So if in the maintenance manual it refers to the wing spar, you know what it's talking about. A little more in depth about truss structures. Truss structures are used, truss structures use struts and wire-braced wings. The occupants sat in open cockpits within a fabric-covered hull or fuselage. Almost all of these airplanes, the truss structure had the engine installed. I don't know why there's a dash there. Had the engine installed up front and auxiliary surfaces mounted aft of the wings to form the tail, also called empennage. Construction of truss-type fuselages to minimize wind resistance and still retain the strength provided by a truss structure. Designers constructed a superstructure of wooden formers and stringers over the framework to produce a more streamlined shape. Formers provide the contoured cross-sectional shape to a structure, while stringers run the length between the formers to fill in the shape. So something you guys should definitely know, how to identify formers and stringers and where they're located in aircraft, how they're used to build truss-type fuselage. This is an example of a Warren truss fuselage. And then we also have stress skin structure. This was the next advance in structural designs. It came with the development of a construction technique that allowed the aircraft to be formed without a truss frame. This design, generally known as stress skin structure. The stress skin structure allowed the aircraft to be built with a more streamlined shape and provided further reductions in weight because the skin itself carried the structural load. When constructed in this fashion, the aircraft was referred to as having a monocoque design. So this is the beginning of what it means to have a stress skin structure in a monocoque design. Again, another good picture of what it means to have, which way your formers run, your longerons, your stringers, and bulkheads. Stress skin, wing, and fuselage construction are divided into two types. So our stress skin structures are either monocoque or semi-monocoque, and these are the differences between those types of structures. So you can review that. Another good diagram of these two types of stressed skin structures. And our truss type wing construction, we have our front inboard here, our front outboard. That's just kind of a simple diagram for you. Truss type wing construction, as far as the wing goes, this is talking about the fabric covered airplane wings utilize truss type structures that have changed very little throughout the design development of aircraft. As with other wing designs, spars are the main load carrying members in a wing truss. I want to put this down here. In the past, spars were mainly manufactured of wood, but the majority of modern aircraft incorporate spars fabricated from extruded aluminum alloy. This is out of your Jeppesen textbook. Has some different types of materials that can be used as shapes for your spar in a truss type wing. This is a stress skin wing construction, so it's identifying you have your ribs here in the wing, stiffeners here, and your main spar here, running down the middle. And moving on to flight control systems. So we talked a lot about flight controls in Theory of Flight. This is some more in-depth information on our flight control systems. Flight control systems govern the necessary inputs to manipulate control surfaces for the pilot to control the aircraft. And the pilot has a set of flight controls to manipulate the aircraft. In the case of many conventional airplanes, the primary flight controls utilize hinged, trailing edge surfaces called elevators for pitch, ailerons for roll, and the rudder for yaw. We also have secondary flight controls that are used in conjunction with the primary flight controls to refine aircraft manipulations further. Additionally, other flight controls not necessarily controlled by the pilot, but serve to produce an aerodynamic effect in flight. Pilots must check the flight control system during pre-flight to avoid known issues. Though flight controls are somewhat standard, they can vary in design and capability from aircraft to aircraft. This is some information on your pre-flight checks. I don't think I added the figure here. Some aircraft may have gust locks that may be removed before manipulating the controls or risk damage. So you can look up what gust locks look like if you have not seen those before. Once these gust locks are removed, ensure the flight controls are free and correct. This verifies that cables are not only connected but done so correctly. You can remember how ailerons deflect by using your thumbs. So this is a fancy little trick. Place your hands on the yoke with your thumbs facing straight up. If you turn left, your thumbs are then pointing left, and you will notice the left aileron up and vice versa of the right. Not if, the right. Flight control malfunctions. Of the two cables that connect any control surface, one of each direction, it is unlikely either, but especially unlikely that both will fail. In the event of such a failure, remember the trim is a separate cable and still has functionality. Through the combination of trim and one cable, you can conduct an emergency no-flap landing. So just some information so that you guys can understand kind of how troubleshooting could work on these flight controls. Flap asymmetry. Flap asymmetry creates an unequal split in the deployment of flaps whereby one side of an aircraft's flaps deploy, but not the other. This can result in a dramatic rolling movement. So to solve this problem, you may attempt to raise the flaps again. Another malfunction can be runaway trim. Runaway trim is a condition in which an electric trim motor has become stuck, causing the trim to move when uncommanded. This can result in a serious flight control problem where the pilot has to muscle the controls to try and maintain a flyable aircraft. The solution is rather simple but complicated at the moment if not considered on the ground. Know where your trim motor circuit breaker is and pull it if you suspect runaway trim. Common training aircraft control characteristics. So these are some characteristics of the Cessna 172 and Piper Arrow. Just some information so that you guys can understand kind of what you'll be dealing with, especially in lab. So on the Cessna 172, single slot type wing flaps. So now you know what that means because of our previous lectures. Adjusted to 10 degrees to 20 degrees to 30 degrees extended. Cessna 172 is protected by a 10 amp circuit breaker. Flap actuator located in the right wing. You actually can see this in the Cessna 172 that we have on the campus. If the actuator cannot function, neither flap will deploy. And Piper Arrow has a plain flap system. The adjustments are 10 degrees to 25 degrees to 40 degrees extended and locked. Can be pulled an additional about 5 degrees but won't lock. Flaps extended and retract manually. And talking a little bit about aircraft assembly, we have some information about aileron installation. I'll let you read through that. This is a brief description of kind of installation, some balancing, and kind of what the maintenance manual will tell you. Same thing for our flap. If you have a flap installation, remember our flaps are a secondary flight control. And if we have an empennage installation, meaning our tail section. The empennage, consisting of the horizontal and vertical stabilizer, is not normally removed and installed unless the aircraft was damaged. Elevators, rudders, and stabilators are rigged the same as any other control surface using the instructions provided in the maintenance manual. You guys will see this. Some of you will run into this when we start removing flight controls. And a little information on our structural alignment. The position or angle of the main structural components is related to a longitudinal datum line, parallel to the aircraft center line, and a lateral datum line, parallel to a line joining the wingtips. Before checking the position or angle of the main components, the aircraft must be jacked and leveled. Small aircraft usually have fixed pegs or blocks attached to the fuselage parallel to or coincident with the datum lines. A spirit level and a straight edge are rested across the pegs or blocks to check the level of the aircraft. That last note there, remember, is for small aircraft. It's talking about small aircraft. Not always the same on larger aircraft. And our structural alignment grid method, sometimes used on large aircraft. The grid plate is a permanent fixture installed on the aircraft floor or supporting structure. That is it for lecture on aircraft assembly and rigging today. I will attach the slides so that you can view them. But you should be taking your own notes during these lectures. Don't forget to take the lecture quiz